quantum renormalization group and its connection to holography. So the ADS-CFT conjecture has been discovered in string theory, and I think at the moment there is little doubt about the validity of the duality. However, we want to have a better understanding about general but we want to have a more general principle such that we can constructively prove the conjecture. Moreover, we want to use the general guiding principle to construct holographic duals for general quantum field theories that may arise in different contexts in nature. So there have been a lot of works devoted to make extract some general principle behind ADS-CFT. And I think from the early days it became quite clear that RRG was behind the correspondence. In particular, the radial direction in the bulk corresponds to the length scale of the field theory, and therefore the bulk variables that lives in space, bulk space and time should be viewed as scale-dependent coupling functions or coupling constants, and the equation of motion that governs the radial evolution of the bulk variables should be viewed as the beta functions, and therefore it basically describes the RG evolution. And that there have been a lot of studies in the name of holographic RG. But I think there is an important a gap in our understanding between RG and holography. So first of all, in RG, the coupling functions or coupling constants are non-dynamical in the sense that they obey first-order differential equation. So if we interpret the radial direction as a time, then it's like a system where kinetic energy is quenched. On the other hand, in the holographic side, we usually have a two-derivative action, and then equation of motion has a second-order differential equation. More importantly, in RG, these coupling functions are classical in the following sense. So if we specify our coupling constants at a UV scale, then we without any uncertainty, we can fix the coupling constant at a low energy scale. So there is no uncertainty or fluctuations. On the other hand, in holography, the bulk variables are supposed to be fully quantum variables. So for finite n, we expect to have non-trivial quantum fluctuations of these bulk variables. Okay, so the claim of this talk is that you can really make the connection between RG and GR precise if we promote our RG to quantum RG. And I will explain what quantum RG means. And even without holography, quantum RG is a really natural framework to reorganize your RG, in at least for large N matrix models. Okay, so for simplicity, let us consider a matrix model where fundamental degrees freedom are some n by n matrix field like large N Yang-Mills theory, or even matrix model with global symmetry. And let's consider an action that is made of a single trace operator. So here ON represents different types of single trace operators that is allowed by symmetry. And Jn of X is a space-time dependent source for each single trace operator. And then I assume that there's some regularization scheme, and then partition function is given by a functional of this space-time dependent source. in conventional RG, what we do is the following. We lower our UV cutoff by some infinitesimal amount and integrate out high energy mode. Then this process modify my effective action, and there are three important terms. First of all, you generate Casimir energy. Since you integrate out your quantum field in the presence of source, you generate source-dependent ground state energy. That's nothing but the Casimir energy. And then, in general, the single trace operator that we had in the beginning acquire some quantum correction. This is nothing but the beta function for the single trace operator. And what's important, first noted, I think, in this paper is that even though you start from a single trace action to the leading order of dz, you always generate a double trace operator in the matrix model. There's nothing wrong with this. You can keep coarse graining your system. However, the problem is that you have to include all multi-trace operators in your RG. So RG trajectory is perfectly classical, and it obeys first order differential equation. But in general, the IR fixed point exists away from the theory where you have only single trace operators. So this plane symbolically represents space of theory, where this represents a theory where you have only single trace operator, where this is multi-trace deformation, and then your IR fixed point exists far away from this plane. That means you really have to solve beta functions for infinite towers of multi-trace operators. There is an alternative way of organizing RG. So the key statement is the following. So this is again the space of theory where only single trace operators are turned on. So initially at my UV theory, I had only single trace operator. And under coarse graining, my theory flow out of the plane. So I have now double trace operator. And then the statement is that partition function of this theory, where I have double trace operator, is equivalent to a theory where you have only single trace operator, provided that the source for the single trace operators are dynamical. In the sense that, in other words, the partition function of this theory is equal to some ensemble of partition function where only single trace operators are turned on. Okay, so effectively, what one can do is to project this theory onto the subspace of single trace operator and give some non-trivial distribution for the source of the single trace operator. So mathematically, this can be done in the following step. So here again, this L prime is the effective action that you obtain after, say, first step of RG, and you have the Casimir energy and the original source, and then quantum correction to the single trace operator, and then double trace operator that you generate. And then this partition function is mathematically identical to the following partition function. Here, if you look at this L double prime, then there is only a single trace operator, ON. Okay? But the price you have to pay is that the source for the single trace operator, represented by small j1, is not a fixed coupling. Instead, we have to integrate over all configurations of this source. And then the rest of the action is designed in such a way that it gives some non-trivial distribution for this source, such that this partition function equals to the original partition function. So let's see how it works. So in this action, say this action is linear in small j1. So this small j1 is a Lagrangian multiplier. So if you integrate out small j1, you have a delta function that enforces the constraint that p1 equals minus on, right? And then you integrate out pn, and then every p in the rest of the action get replaced by o. So this p squared term become O double trace operator, and this P linear term become this O linear term, quantum correction. So it's very easy to see that this is an exact mathematical identity. So physically what happens is that you have, you in RG, you divide your mode into high energy mode and low energy mode. And then these high energy modes have non-trivial fluctuations. And from the point of view of the low energy mode, these fluctuations of the high energy mode acts like a dynamical source. Okay? And this is encoded in the fact that this source seen by the low energy operator is dynamical. And then dynamics of the fluctuations of this source is controlled by what you have integrated out in your RG procedure.
This is more similar to an Hilbert-Sutton.
Yeah, you can view it as a Hilbert transformation. Okay. So, and then you repeat this procedure. So you start from UV theory, you coarse grain, you generate double trace operator. Now you project to the space of single trace operator by introducing this dynamical source and its conjugate field P. And then at the end point of any of this theory, you coarse grain again, and then generate double trace operator, and you project to the single trace theory by introducing another set of dynamical source, and so on. So at the end of the day, your partition function can be written as functional integrations of this dynamical source and its conjugate field introduced at each step of RG.
Next step, will the Lagrange multiplier you introduced in one step actually become dynamical? That is, it'll get a kinetic term from radiative correction?
That's right. So here, this was a pure Lagrangian multiplier. But now you integrate high energy mode that couples to this source, and it generates Casimir energy for this source. So then it's no longer a Lagrangian multiplier. It's a genuinely dynamic. It's very similar to what we have learned in condensed matter physics when we use slave particle theory. So you introduce gauge field as a Lagrangian multiplier to impose some constraint. But as you integrate out some high energy mode, this high energy mode generate dynamical action for the gauge field. And under certain circumstances, this dynamical gauge field really become deconfined and become propagating mode. So similar thing happens here.
Is that how I'm supposed to think of that direction in the sort of holographic picture, as sort of going further and further
RG
about
direction.
and then rewriting the theory on that slice?
Yeah.
Okay.
Yeah. So this step become radial direction. So I make this step size smaller and smaller and make infinitely many steps. So then this 1, 2, 3, this RG index become extra dimension. So the picture is that the advantage of this RG is that you don't need to worry about multi-trace operator in your RG. Your RG is completely formulated in terms of single trace operator. The price you have to pay is that you have to include quantum fluctuations for your RG path. In other words, your partition function is given by sum over all RG paths. And then each RG path is weighted by some action that you can derive from your beta functions, from your Casimir energy and beta function of your QFT. And then, as I said, this discrete RG index become continuous radial dimension. So therefore, this action that governs the fluctuation of dynamical source is naturally d plus 1 dimensional action for this dynamical source and the conjugate field. And then the information that you need to know to construct this holographic action is basically the Casimir energy, as Sean pointed out. If you integrate out high energy mode that is coupled to dynamical source, then it generates Casimir energy for your dynamical source. Usually in usual RG, this Casimir energy is not, we don't pay much attention to it because it's just the overall constant. But here it's very important because it gives dynamical action for your fluctuating source. So that is this piece. And then the beta function for the single trace operator in the presence of only single trace source. So that contributes to linear term in P. And then beta function for the double trace operator, again in the presence of only single trace source. That provides the coefficient for the quadratic term in P. Okay? It's very tempting to interpret this radial direction Z as a time, some kind of time. Then you can view this term as a Hamiltonian, quantum Hamiltonian that governs the radial evolution of your quantum coupling operator. Okay. And then this Casimir energy basically provides the potential energy for the source. And then this beta function, especially the beta function for the double trace operator, provides the kinetic energy for the momentum. Okay. So then question is, can we really see gravity emerge from this picture? So the answer is yes. And in general, if you apply this procedure to general matrix field theory, the bulk action that you get is very complicated because you have to introduce dynamical source for every operator that you can turn on in your theory. But to see how gravity emerges in a simplest context, let us assume that we have some idealized field theory, and this is some matrix field theory, and it's a very strongly coupled theory. So this theory has a Poincare symmetry so that energy momentum tensor, the scaling dimension is protected. But suppose there is no other symmetries, therefore all other operators acquire very large anomalous dimension. So suppose all other operators except for the energy momentum tensor has infinitely large scaling dimension. So this amounts to saying that under my coarse graining, even though other operators may get generated, they instantaneously decay. So that my RG is self-contained within the subspace of operators that can be constructed from energy momentum tensor and composite operator of energy momentum tensor. Okay? So let's assume that such theory exists. And then again, this is the single trace theory, and this is multi-trace deformation. In general, the fixed point, IR fixed point of this theory will exist with some complicated multi-trace operator. But instead of thinking about this fixed point, let us consider a projected fixed point. So projected fixed point means a fixed point for projected RG flow. Projected RG flows are RG flow that is projected into the subspace of single trace operator. Right? And then you can think of a point at which this projected beta function vanishes. Of course, this is not the real fixed point because at this fixed point you can have a non-trivial, non-zero beta function, but that's only along the multi-trace deformation. Okay, so you don't have to, but it's convenient to start from this theory. And then suppose we add some energy momentum deformation because that's the only low dimension operator, and adding deformation of energy momentum tensor is equivalent to turning on some non-trivial background metric in your theory because metric is the source for energy momentum tensor. So let's put your theory in some general curves background space and time. So G0 is not dynamical metric, it's a fixed metric in the d-dimensional space and time. And then this S1 is the single trace action. Okay, and then the partition function is of course a functional of this metric. And I'm assuming that there is some regularization scheme that respect the d-dimensional diffeomorphism invariance. In other words, I'm assuming that this partition function has the word identity associated with the d-dimensional coordinate transformation. Okay, and then we coarse grain the system again. We integrate out high energy mode and lower the UV cutoff, and we scale my space and time, and that in this context that amounts to changing your metric. So by changing your metric, you effectively decrease you increase your length scale. So that is kind of a knob that I turn to run my RG. So this is and then changing the metric is equivalent to adding some single trace deformation again, the energy momentum tensor deformation, and then we would want to choose this A mu nu to be proportional to G mu nu. So that is just the dilatation of your metric. So we change our scale, and then as I do that, quantum corrections are generated. So the first, and then one more important thing is that usually we change our length scale in RG uniformly in space and time, but you don't have to do it. You can choose the warping factor to be space-time dependent. So I'm choosing this ND is the speed of RG, speed of coarse graining, and I choose this speed of RG to be space-time dependent. Okay, and then quantum corrections are generated. So first again the Casimir energy, and then as was noted by Sarov in 60, we integrate out high energy mode in the presence of background metric. Then you generate gravitational action for the metric, background metric. Okay, but here and then I include only two derivative terms here. There are higher order derivative terms, but up to two derivative level, you have some constant piece, and also and then the Ricci scalar. And important thing is that this is a Ricci scalar for the d-dimensional metric. So this is not yet d plus 1 dimensional gravity. So this is just the Casimir energy. And then important.
What scale suppresses the R squared terms?
The UV cutoff in general, unless you have some special property in your theory. So here, only scale that I have is a UV cutoff. And then, as I said, in general, you generate double trace operator, T mu nu and T rho sigma, and then this is the beta function for the double trace operator. Okay. Now, as we did before, we introduce auxiliary field to dynamical source, but in this case, source for energy momentum tensor is nothing but metric. So dynamical source is basically dynamical metric. And then introduce conjugate field to remove the double trace operator. And how do we do it? Preserving the d-dimensional diffeomorphism invariance, we can do it. So before we do that, let's consider another. Let's exploit another freedom in our RG. So again, in conventional RG, when we coarse grain, we assign same coordinate to the low energy field as the coordinate of the high energy field. But we don't have to do it, especially because low energy fields will be coupled to dynamical metric. So we can choose to assign different coordinate for the low energy mode compared to the coordinate of the high energy mode by shifting the coordinate by some infinitesimal amount. So this n1 mu. So this is the shift of the high energy mode in the first step of RG along the mu direction. Okay, this is purely my gauge choice. It's my choice of coordinate. Okay, and then a shift of the coordinate is equivalent to changing the metric by some amount, and this introduces another correction to your action. And this kind of RG dependent shift has been first considered, I think, in this paper. Okay, and then, as I said, we introduce this auxiliary field. So here, G1 mu nu is now the dynamical d-dimensional metric, and pi mu nu is the conjugate field. And then it's easy to see that this is equivalent to the previous theory with double trace operator. So for example, so what is the energy momentum tensor? Energy momentum tensor is nothing but the derivative of your action with respect to your metric. Okay, so every energy momentum tensor that you have in S1 prime and S1 double prime in quantum correction, so this includes the double trace operator of energy momentum tensor, This includes the single trace energy momentum tensor, and you replace it by the derivative with respect to your metric. And then this pi 1 in this case is nothing but the Lagrange multiplier that forces this dynamical metric G1 to be the original metric G0. Okay? So after applying this derivative to this action, every derivative gets replaced by energy momentum tensor, and then you integrate out pi 1 and G1, and G1 becomes G0. Therefore, it's nothing but the original theory with double trace operator turned on. Now, what we can do is to do the integration by part for this functional integrations of the metric. And then if you do that, this now derivative with respect to metric acts on left. And on the left, I have this term in the exponential. So whenever I apply this functional derivative with respect to metric G1, I get minus I times pi 1. Okay? So in other words, every energy momentum tensor that I had in this quantum correction get replaced by this pi 1. So this is basically what we had in the general picture. So at the end of the day, my partition function is now written as a partition function for the theory where I have only single trace operator S1, but at this time this is coupled to dynamical metric G1. So metric is fluctuating G1, and then the distribution of the metric is controlled by the action generated by this beta function. Okay, so in particular, in the beta function for the double trace operator give a quadratic action for pi. Therefore, pi is not a Lagrange multiplier. And then if you integrate out pi, for example, you will get some Gaussian distribution for G1. So you have to sum over some configurations of fluctuating metric. And then now you repeat the same procedure for this action. You coarse grain, you generate double trace operator again, and then you can choose your shift at your convenience, and then again introduce another set of dynamical source and conjugate field, etc. So if you keep doing this, then you get the following bulk action. So again, so this metric and this conjugate field is like a canonical conjugate to each other if we interpret this radial evolution as a time. And then this n mu is the shift that I introduced, the shift of the coordinate at each slice of my RG. And in general, this is this can be dependent on full d plus 1 dimensional coordinate, because I can shift differently at different scale, and I can shift differently at different point in space and time. And likewise, this is the speed of RG, and speed of RG is also a d plus 1 dimensional function in general. And this is so-called momentum constraint is very straightforward. It's universal. It's just determined by how metric transforms under coordinate transformation. And when you have when you keep d-dimensional diffeomorphism invariance, this is completely fixed. So what is non-trivial is the coefficient of this lapse, the speed of RG. So as I said, this is like a Hamiltonian-like object, and it includes two parts. The first is the Casimir energy, and this includes the constant piece and d-dimensional which is scalar, and also higher derivative term. And there is a kinetic energy-like term that is quadratic in P. This is generated from the double trace operator. So previously I wrote the coefficient of pi mu nu, pi rho sigma as some general coefficient b mu nu, b rho sigma. But the d-dimensional diffeomorphism of the two derivative level only allows this form. So you cannot have other forms of the kinetic energy if you have d-dimensional diffeomorphism invariance.
Can you explain what fixes that -1 for the second term? I mean, why does if the pi mu nu term, if I change that coefficient, why does it not respect diffeomorphism invariance?
Sorry, this coefficient?
Yeah.
So yeah, so this, I have only one relative, this alpha is a relative coefficient, and then I can choose my overall scale to make the coefficient of this to be 1, basically.
You can rescale that purple box relative to the green box?
Yes, yeah. Then only degrees freedom that I am left with is the relative magnitude between
I see, by redefining.
pi square and pi mu. And this coefficient is not fixed by d-dimensional diffeomorphism invariance. And this kind of action has been considered a lot in the context of non-Einstein gravity, example, Holography gravity. And then there have been a lot of discussion what kind of parameter is allowed here.
Is this the lambda parameter in Holography gravity?
Yeah. And then, but however, in this case, there is a constraint. The constraint comes from the fact that I have gauge freedom. In other words, my partition function is independent of the speed of RG that I have chosen, and it's also independent of the shift that I have chosen. So these are pure gauge freedom. So these are RG prescription. And whatever RG prescription you choose, if you do exactly, you have the same partition function. That means the partition function should be independent of your choice of lapse and shift, and that means the coefficient of this lapse and then shift is actually constrained. They vanish on shell. On inside average, they have to vanish. Okay. Moreover, this constraint has to be satisfied not only at a time, but at a certain radius, but all radius, no matter how you choose your lapse and shift. Okay. This is obvious from the fact that these are pure gauge choice. That means the radial derivative of this constraint has to vanish as well, and that means the Poisson bracket between this constraint has to vanish again on shell. So this is exactly the condition for the first class constraint. Okay. And then if you impose this constraint, then this alpha is actually uniquely fixed, as was shown by these people from the context of Holography gravity. And this in d-dimensional space-time, this has to be 1 over d minus 1. Okay, and then if you now integrate out pi mu nu, then you exactly reproduce the Einstein-Hilbert action in d plus 1 dimensional space and time, up to 2 derivative term.
So like in Hegel, there would be time rail direction, you would have a global time foliate
Right.
space-time,
Right.
right?
Yeah. Right. It's like a Hamiltonian formalism of your gravity, where the radial direction plays the role of time. It's the boundary time is there, but this is like space-like time. And then so this is a partition function, and then can we make a connection to wave function? And you can. For example, in field theory, the ground state wave function is given by Euclidean function integrations with boundary, where you fix your field at the boundary to be certain configuration. And this quantity is a functional of the field configuration at the boundary. And this is nothing but the ground state wave functional of your field theory.
Can you play something on the previous transparency? Okay. Just from holography, I would have expected that you would end up with some hideous non-Einstein theory of gravity if you did RG for a general abstract field theory.
You mean higher derivative terms?
Yeah, but in answer to my earlier question, you said they were actually suppressed by a high scale.
No, actually, yeah, so I have to mention it. So here, this cosmological constant and also these higher derivative terms are all controlled by UV cutoff. That means in general theory, the curvature scale and then the non-local scale of your derivative are comparable. Right. So in that sense, it's quite non-local for general field theory. So you should have some additional tuning parameter if you have some exact marginal operator, something
You're saying
like
the curvature will be at the cutoff, so higher terms aren't suppressed at all.
That's right. Yeah.
Even with this assumption that there's only the stress tensor and it's descending?
Yeah, that's puzzling. So why this assumption that I have only energy momentum tensor as low energy operator is not enough? to separate the cosmological constant from higher derivative term. But in this scheme, it appears that there's no reason why they have to be separated. Maybe
There should be a large n there.
large n is different thing. Large n controls the quantum fluctuations. So, and in the matrix model, n square controls the quantum fluctuation. But the higher derivative term, even at the classical level, they are important here.
Presumably there's something else that could break down, which is sort of, I mean, if you have sort of the Heidegger regime, everything goes through, but if you start having high curve, what would lead to high curvatures in the bulk, like in Larry's talk, you know, you have these caustics very near to the boundary or something.
Right.
So presumably the RG flow also somehow breaks down or something happens to it, right?
I think it's not that it's breakdown. It means that higher derivative term become important. Yeah. So the truncation is not accurate. Yeah, you cannot truncate your action up to 2 derivative term in that case.
I think if you assume you only have independent tensor and the central charge is large, then it'd be done, I guess, no? 'Cause then wouldn't C0 be small?
So you think this higher derivative term should be suppressed?
No, you need the cosmological constant. So isn't the central charge like L over L Planck or something?
So here, central charge is like it's controlled by n squared. But this higher derivative, the higher I don't know why. Yeah, somehow, that question depends on, I think, specific field theory. This is just a generic feature.
Can I just add something to Sean's comment? I mean, it's known in the case where you have 4-dimensional conformal field theory, you know if the A and C anomalies don't match, that you can't realize it with just Einstein gravity, right? So Sean's comment could never be enough on its own.
So can you say?
So in a 4-dimensional conformal field theory, if the A and C anomaly don't match in a large n limit, it cannot be realized by Einstein gravity.
I see.
So you know that you need something more than what Sean said. You need a little bit more to insist that you're on Einstein gravity.
You mean you need the higher derivative?
What you're saying, I think, is that in some dimensions there are Gauss coordinate, there are other ways of having saying just second derivative is not unique.
Right. Yeah. So they are say 4 derivative terms. They can be important, and they will determine central charges A and C. But so probably that means even though you only assume energy momentum tensor large n, that doesn't uniquely specify your bulk action.
You require a little bit dynamics, right? If you have incontrollable super Yang-Mills theory, should C0 be independent of your UV cutoff?
Which one?
C0.
Oh.
If C0 is independent of your UV cutoff, then your low energy theory will be just Einstein gravity. Then all your higher derivative terms then they're just suppressed, and then the low energy theory will be Einstein. Then will be you have to determine the sign also, but otherwise it will be just ADS. Yeah, but that is require dynamical input.
Yeah, that's the dynamical input. Yeah.
In this example, with just the stress tensor, I mean, the fact that you write n squared, it doesn't. I mean, the matrix nature of this sort of phantom CFT, where does that enter into these calculations?
Where does
Where does that enter into everything that?
Yeah. So here I normalized this energy momentum tensor to the order of 1. Therefore, in the action, you have n squared over a factor. That 1 over n squared plays the role of Planck constant.
But I can make it an n, say.
M?
I can make it an n instead of an n squared, and everything would still work.
No, not for the matrix model. For vector model, you would have n.
Right, exactly. So, but everything we're seeing here, how sensitive is that to the fact that you're claiming to consider a matrix model?
So as I said, for matrix model, this has to be n squared. For other model, it can be different. For vector, large n vector model is n.
The beta functions for the double trace operators are down, and he's assuming that relative to the beta functions for the single trace operator.
By n squared.
But they are equally important as single trace operator. So you cannot, even the large n limit, you cannot ignore double trace correction.
But if you had an ungauged theory with
even in
squared degrees of freedom, it wouldn't have worked. You wouldn't have had the separation into single trace and double trace operators. You need the gauge symmetry.
you need so say in the larger image you have a separation. Okay, so this is the wave how we think about the ground state wave function in field theory, and then this is like a partition function with boundary condition, and we can apply this holographic construction to the wave function. So here I'm assuming that there is a covariant way of separating high energy mode and low energy mode. Say most simplest picture is like I consider some wave vector that along the space direction, and say at high energy I integrate out those modes with momentum share between lambda 2 and lambda 1 and etc. So if it's not clear whether all theory can be think in this way, but if there is a covariant way of separating high energy mode and low energy mode, then the ground state wave function can be written as a d plus 1 dimensional functional integration of the source with some boundary term that depends on your field configuration. Okay, so this is a holographic way of thinking about a wave function. Okay, so maybe the MERA is some kind of time slice version of this. There is some connection, but it's not entirely clear. And then in this context, you can think about the density matrix. In particular, this quantum RG now allows us to really go into bulk. For example, we can think about entanglement between, say, low energy mode and high energy mode. Suppose now, starting from this ground state wave function, suppose I trace out the low energy mode. Okay, and then the density matrix will look like this. I have two edges, and then my boundary configurations are defined on these two edges. And then if you want to compute entanglement entropy between, say, low energy mode and high energy mode, that's equivalent to, in the replica trick, equivalent to inserting some deficit angle along this edge. So in this construction, it's very obvious that metric, so entanglement entropy is nothing but the metric response of to this deficit angle. So it's so entanglement is encoded in the geometry, in a very obvious way.
What is this edge?
So this is the edge. So suppose I want to know the entanglement between mode above this scale lambda 3, and then the mode below this scale. Then I trace out the mode below this scale. Right?
So you make a direct identification of the k with the z.
Yeah, right. So here I'm choosing one particular gauge choice. So I divide my low energy mode in terms of k.
But typically below, at least from your previous calculation, you cannot make this.
So I'm not sure whether this can be always done. But if I choose this description, if I insist that my high energy mode here have momentum only in this range, and so on, and then so maybe the subtlety is you cannot, for example, in the gauge theory, you cannot really divide your high energy mode and low energy mode in a gauge invariant way.
Right. That seems to be completely against the philosophy of the earlier derivation, which you actually don't need to do this kind of thing.
Yeah. So, but yeah, that's right. We don't need to make that choice, but we can.
No, it's not clear you can actually in the certainly in possible Yang-Mills.
Yeah, right. So but for non-gauge matrix model, you can choose this kind of thing. But it's less obvious how one can do that in gauge theory. But maybe in gauge theory there must be some non-local constraint on how this field configuration can be arranged. So in a sense, this mode may not be completely independent from the mode inside bulk. But if one can do that, then you can think about density matrix, and also you have a tool to think about the entanglement between low energy and high energy mode. But this is just rough statement. So in summary, the quantum RG, I think, provides a general and microscopic picture for a DSFT correspondence. And apart from holography, quantum RG, from RG point of view, is another way of maybe more efficient way of organizing your RG for large and matrix model. And then under certain assumption, up to 2 derivative level, you can explicitly see that Einstein gravity emerge in the bulk. Okay, so that's the end. Thank you for your attention.
Have you thought about what black holes would look like, starting with the thermal state in this framework?
No, I want to, but I don't really know how to. So, yeah, I think this is an attempt to go toward that direction. Maybe. Yeah, you know, here in prior there's no brain. Some quantum gravity.
Any more questions?
Yes, please. I just want to understand, at what step did you really need to be considering a matrix system?
So okay, so the matrix model is unique in the sense that when you have only single trace operator in your beginning, you only generate double trace operator. So that makes your kinetic energy to be quadratic in P.
I see.
For non-matrix model, so you can always, for general field theory, you can always choose a set of primary fields from which you can construct any operator as a composite operator. But in those cases, this kinetic term will not be quadratic necessarily, because there can be very nonlinear relation between operators.
Yes, please.
There should be something for conventional field theories that fixes the sign of your cosmological constant to be negative.
Right.
Do you have any idea what that is?
No, I don't. So maybe, I don't know what feature of field theory determines the sign of the Kashim energy. If you know, if any of you know some constraint, that will be very interesting. But here, the cosmological constant is nothing but the Kashim energy of your field theory. Maybe, I don't know whether one can get some. If this was positive, then maybe one can have an even distal space, the bulk.
Would it be somehow related to the sign of the determinant of the metric on the slide?
Yeah, this is, so even though you fix your metric to be Minkowskian at your slice, this sign can be either thing depending on the sign of Kashim energy of your field theory. Maybe it depends on the number of fermionic and bosonic matter field in your theory.
Any more questions? There's no questions. We continue the slide. I think let's take this.